Welcome back, fellow explorers of the universe. Today we journey into the hidden structures of plasma and the forces that shape it. In this video and the next, we are laying the foundation for Birkeland currents, one of the most important yet misunderstood plasma structures in space. Today we are focusing on four key aspects. First, we will look at plasma filaments and explore how plasma naturally forms long, thread-like structures. Then we'll examine plasma pinches and how electric currents cause plasma to contract into tight channels. Finally, we will discuss energy transfer in plasma, specifically how energy moves through plasma via Alfvén waves and magnetic reconnection. For each of these topics, we will briefly define what it is, give real-world examples of where we see it in nature or the lab, and explain why it matters, especially in relation to Birkeland currents. And if you enjoy exploring plasma phenomena and the hidden forces shaping our world, be sure to subscribe and hit the notification bell so we can uncover these mysteries together. Now let's start by looking at the first key feature of plasma's hidden architecture. These plasma filaments are observed across a vast range of scales, from high-energy laboratory experiments to cosmic structures spanning millions of light-years. Plasma filaments form when charged particles move along magnetic field lines, carrying electric currents that generate self-reinforcing magnetic fields. This process follows Ampere's law, where the current flowing through plasma creates a surrounding magnetic field that constrains the charged particles into a narrow structure. Plasma's high conductivity allows these currents to remain stable over long distances, forming extended filaments in space. Now let's look at where we can find these plasma filaments in action. Galaxies and galaxy clusters form along vast plasma filaments that stretch across space, creating the cosmic web, which serves as the scaffolding of the universe. These filaments act as conduits for charged particles and energy flow, playing a crucial role in star formation and cosmic evolution. Observations suggest that magnetic fields guide these structures, meaning that electric currents could be shaping the cosmos at a fundamental level. On Earth, lightning strikes follow filamentary paths because ionized air creates a conductive channel for electrical discharge. High-altitude discharges, like sprites and blue jets, also exhibit plasma filament structures, revealing complex electrical interactions between Earth's atmosphere and space. Similar behavior is seen in volcanic lightning, where ash particles ionize the air, allowing plasma channels to form. In interstellar clouds, these dense filaments in nebula serve as pathways for gas, dust, and plasma, significantly influencing how stars are born. Magnetic fields interact with plasma in these regions, creating filaments that funnel material into protostars. Astronomical observations show that interstellar filaments align with large-scale magnetic structures, revealing how plasma filaments shape stellar nurseries. These are just a few examples. Plasma filaments also appear in solar prominences, auroras, the Earth's corona, and laboratory plasma experiments like tokamaks and Z-pinch devices. Now that we understand how plasma filaments form, let's explore how these filaments can tighten and concentrate energy, a process known as the pinch effect. The pinch effect occurs when electric currents flowing through plasma generate magnetic fields that compress it inward, increasing both its density and temperature. The inward force exerted by the plasma's magnetic field causes it to tighten, following the Lorentz force, where charged particles moving through a magnetic field experience a perpendicular force. As the currents increase, the inward pressure grows stronger, forcing the plasma into a thinner, more concentrated channel. This exemplifies self-organization in plasma, where electromagnetic forces govern the structure and dynamics of the material. A good example of the pinch effect in plasma is the Z-pinch in plasma experiments and fusion research. In a Z-pinch, electric currents pass through plasma, creating magnetic fields that compress the plasma inward. This process forces the plasma to become denser and hotter, which is crucial for achieving the conditions necessary for nuclear fusion. The Z-pinch effect is used in laboratory settings to create high-temperature, high-density plasma, which mimics the conditions found in stars, including the Sun. This process is one of the key applications of the pinch effect, as it shows how plasma can be constricted by its own magnetic fields, leading to energy concentration and potential energy release. Now let's look at high-energy jets from black holes and neutron stars, and how they exhibit long, structured plasma streams that extend across interstellar distances. These jets remain coherent over vast distances, suggesting that magnetic forces are stabilizing and guiding them, much like the pinch effect in plasma dynamics. Similar behaviors are observed in supernova remnants and pulsar winds, where magnetic forces cause plasma to constrict, concentrating energy. Beyond these examples, the pinch effect is also observed in lightning channels, laboratory arc discharges, and certain types of plasma propulsion systems, where magnetic forces compress and guide the plasma into concentrated structures. Understanding how plasma naturally constricts is crucial in astrophysics, fusion research, and space plasma physics. These forces explain how plasmas release energy explosively, from solar flares to supernova. Most importantly, this behavior helps explain the structure of Birkeland currents over vast distances. So far, we've explored how plasma forms filaments and how those filaments can tighten and concentrate energy through the pinch effect. But now let's look at how energy moves through plasma using two key processes, Alfvén waves and magnetic reconnection. Alfvén waves are oscillations in plasma where magnetic fields act like tension strings, transmitting energy along their lines. These waves occur when magnetic tension pulls charged particles back into place, creating a wave-like motion similar to how a plucked guitar string vibrates. Since plasma is highly conductive, these waves allow energy to be transported across immense distances without significant loss. Where do we see Alfvén waves? One example is in solar wind acceleration. The solar wind is a continuous outflow of charged particles from the sun traveling at hundreds of kilometers per second. Alfvén waves provide energy that keeps the solar wind moving, preventing it from collapsing back toward the sun. These waves propagate outward, transferring momentum to the charged particles and accelerating them into interplanetary space. Without this mechanism, the solar wind wouldn't reach the speeds necessary to shape the heliosphere and influence planetary magnetospheres. Another example is the stunning auroras. When charged particles from solar wind interact with Earth's magnetic field, Alfvén waves form and guide them toward the poles. These waves act like conveyor belts, transferring energy that accelerates electrons and directs them into the upper atmosphere. The excited particles collide with atmospheric gases, producing colorful light displays known as auroras. Beyond these examples, Alfvén waves are observed in fusion reactors, astrophysical plasmas, and even in turbulent plasma environments throughout the universe. Now let's move on to magnetic reconnection, which occurs when tangled magnetic field lines break and reconnect in a new configuration. This process converts magnetic energy into kinetic and thermal energy, producing sudden bursts of high-energy plasma. Reconnection events can cause some of the most powerful outbursts in the universe, from solar flares to explosive astrophysical phenomena. Where do we see magnetic reconnection? One place is Earth's magnetosphere, where magnetic reconnection occurs when the solar winds interact with Earth's magnetic field. This process causes the magnetic field lines to break and reconnect, releasing energy in the form of high-speed charged particles. These particles accelerate towards Earth's poles, contributing to the stunning auroras we just spoke of. This magnetic reconnection also plays a key role in space weather, impacting satellite communications and geomagnetic storms. Another example is neutron star magnetospheres. Neutron stars have some of the strongest magnetic fields in the universe, capable of driving violent reconnection events. These reconnection-driven outbursts are observed as magnetar flares, where sudden realignments of magnetic fields release enormous amounts of energy. The process is so powerful that it can temporarily outshine entire galaxies in certain wavelengths of light. Studying these extreme reconnection events helps us understand the limits of plasma physics and the role of magnetism in high-energy astrophysics. Magnetic reconnection is also observed in astrophysical jets, solar flares, and controlled fusion experiments. Now that we've explored how plasma forms filaments, tightens through the pinch effect, and transfers energy through Alfvén waves and magnetic reconnection, let's take a moment to put all of these concepts together and see how they relate to Birkeland currents. As we discussed, plasma filaments are naturally occurring structures in plasma that serve as pathways for electric currents throughout the universe. Birkeland currents, which are large-scale plasma filaments, carry electric currents by moving charged particles between planetary magnetospheres and solar wind. Plasma pinches occur when electric currents flow through plasma, causing it to contract into denser, more concentrated structures. This ability to self-organize helps Birkeland currents remain structured over vast distances. Alfvén waves allow plasma to transfer energy efficiently along magnetic field lines. Without them, the charged particles in Birkeland currents wouldn't be able to move as smoothly across space as it does. Magnetic reconnection reshapes plasma currents by breaking and reconnecting magnetic field lines, releasing stored energy. This helps explain how Birkeland currents interact with planetary magnetospheres, contributing to space weather and auroras. All of these forces, such as filamentation, pinching, wave-driven energy transfer, and reconnection, work together to shape Birkeland currents, making them stable, structured, and capable of moving massive amounts of charged particles across space. In the next video, we'll go deeper into how Earth's magnetosphere functions as an electric circuit. We'll also explore double layers and plasma sheaths. By the end of this series, you'll not only understand Birkeland currents, but many of the terms and concepts often used when talking about plasma or plasma physics. And thank you so much for joining me today. If you enjoy exploring plasma phenomena and the hidden forces shaping our world, be sure to subscribe and, most importantly, hit the notification bell so we can always uncover these mysteries together. And until next time, take care.